So let's continue that talking about bending stress. And so as I look at my cross section here, there's my neutral axis. I have my C value to the bottom surface. I have my C value to the top surface. And as we're dealing with this, the top was in compression, the bottom was in tension. So this is our neutral axis, compression, tension. So now via statics, as I was talking about, we have to make sure that this all balances out. So I have a force going on. So I have more than just a force, though, because it is separated by distances. So I am going to have some moment. So I have some resultant moment, and that's going to be equal to the moment that is produced by the stress. So what is a moment? A moment, as we remember, is the force times the lever arm. And so that is going to produce a moment. And so what is the moment? Well, we'll look at a differential element of moment. And so the forces will be a differential element of force times the lever arm. What's the lever arm going to be? Well, we've either got positive y going this way, negative y going this way. So it would be the distance y. Now, just something for naming conventions. So on the side that is going to be compressive, so in this case we're bending up. Positive y would be the y direction that's going to shorten the distance, where negative y is going in the other direction. So it's basically positive y is going in the direction of the bend, so it's towards the compressive side, where negative y is going to be going away from the bend, which will drop it to the tensile side. Okay, so now we go back and look at this, and okay, so our d moment is going to be that df times y. So my resultant moment is going to be equal to the sum of all the little moments that we have based on those stress values. And so if we sum up all those moments based on the stress values, what is that really? Well, that's just going to be the integration over the area of the moment, which will be negative y times df. And as we looked at it before, I know that df is stress times dA. So I'm going to integrate over the area, negative y, stress dA. And once again, we're assuming a linear elastic relationship and assuming that we're in the linear region. So I can replace that stress with negative y over c, stress max. And we're going to integrate that all over the area. So once again, just like before, I want to pull the constants out here. And so this moment, this resultant moment for everything, stress max is going to come out because that's not based on the area, and neither is c. And so what we're left with is negative stress max over c, because we'll pull that negative 1 out, y squared dA. So do you remember what the integration over the area of y squared dA is? So if we go back to mechanics, y squared dA, it's not going to be the centroid, but it's going to be the moment of inertia of the cross-section. So moment, I'm spelling that wrong. I was looking at it going, huh? So moment of inertia of the cross-section. So a moment of inertia cross-section is something that you will look up. You can look it up in a book. You can calculate it out using the parallel axis theorem. And I apologize for that. I'm sure that you guys heard that my German Shepherd looked out the window and my neighbor parked the car, which obviously means they're here to kill us all. So she had to bark at them. As I was saying, the moment of inertia of the cross-section, you can look it up in the equation manual. You can calculate it out for the parallel axis theorem for more complex shapes, which we will be doing. So we'll review that in one of our problems. But the moment of inertia, what is moment of inertia? It's basically a measure of how difficult it is to spin something around that particular axis. Oh, I did not mean to end the slideshow. Let's go back one. So what happens if I put this all together? So if I put this all together, I can calculate out the maximum shear stress. And so, actually, I put this negative in here. That shouldn't have happened because we have a negative and a negative which cancel out. Sorry about that. I was getting ahead of myself in a different formula. And so what we have is, okay, well, that maximum stress is, that moment is going to be the maximum stress over C times I, which will typically be written as the stress max is going to be equal to MC over I. And we'll box this because this is an important equation. So this is what's called the Flexure formula. Well, this is one of the two Flexure formulas. So remember, C is the maximum distance from the neutral axis to the outside surface. So you can have you'll have two different stress maxes. One for the tensile stress, one for the compressive stress, depending on what it's going to be. And just one thing to remember, since stress is equal to negative y over c of stress max, the other Flexure formula, when we're looking at what the stress is at any point within the cross-section, will be the stress is negative my over I. And so that negative interaction comes in there. That's why we have to use this dimensional convention to where, as we're positive is going towards the compressive direction, which will give you a negative stress, where going away, so the tensions in the negative direction will give you a positive stress. So these two are the Flexure formulas. And I know things got a little confusing there, so I will not only box them, highlight them, because these are going to be the main formulas that we will be using to calculate out stresses in a pure bending situation.